Actually, this is the tools which were already developed. Is called a long time ago. It has a long history of development. It is based on micromechanics, but we're not going to cover much about the micromechanics. Basically, this is the as it says in title, Hanyang Classical Laminate Theory, HICLT. This is the tool we can analyze the laminate composites.
교수님, 그 화면 공유 잘 안 됩니다. 화면 공유 잘 안 됩니다.
Okay.
네.
So the last week, we just shared the final equations, and this is the we briefly defined the in-plane and bending load, which can be applied to laminate. It's called N and M. And then how much it deform? We have epsilon 0 and curvature. Okay. Okay, I will open the class notes. Just 1 second. But it takes some time to get downloaded. I will briefly go through the structures of this Excel file. But it is very much structured. As you can see, here is the first column, and it has a lot of information containing all the material property and etc. And exactly same format. This is gonna second column and third column, and up to 52 columns. In fact, each column represent each ply. So in this case, we can cover up to 52 plies, and each one will have information of the what material and what angles and etc. That is basically the structures. And on top, we have the three load, in-plane load, and three bending load, and three bending. And there are four, one, two, three, four choice as an input. We call load option. If we enter number one, means that we're gonna enter this one as the input. This is gonna be option one, and if option two, then we're gonna have a N and K. Sorry, two for the N and K. N means the in-plane load. K represent the curvature, and 3 for epsilon and curvature, and 4 means the another options. So and let's say we will come to these options more later on. We'll discuss more about the other options, but today let's focus on the option one. Option one means that, as discussed the last time, we are entering load N2, N1, N2, N6, and moment to 1 to 6. So this gonna be an input in red, and this will be the output. So I'm gonna just try, and as you can see, you can have some result. Actually, just pay attention to this and this. So this gonna be input, and this gonna be output. And well, this is not so much clear expression, but again, we have a load and in deformation, and between them there is a matrix. So okay, let me open this file. Okay, well, this PowerPoint will be shared later on. It is a lecture note covering the major theory of the classical laminate theory. And chapter 4 is the kind of a final form of this theory. I will just briefly go through. As we discussed last week, there is a laminate which consists of many plies stacking from the bottom, 1, 2, 3, 4, as many as you like. In Excel file, I just mentioned that we can layer the up to 52 plies. And then this laminate will deform an in-plane load, in-plane deformation, which will be uniform through the thickness, and then there will be a curvature. Um, all the strain is linear through. Just 1 second. Don't know why. So this is the in-plane strain in any positions, and this is the in-plane strain, and this is a curvature, and there is a z. We briefly discussed last time. So epsilon 0, actually epsilon represent the three strain, in-plane strain, and K is the curvature. Notice that there is a z multiply each strain component. And so in here, these K1, K2, and K6 each represent the bending and twisting. K1, K2 represent the bending. K1, K2 is relatively easy to understand. Strain is the function of a z through the thickness, and there K1 is the curvature. And now twisting is relatively difficult to understand, but same concept, but in this case, in-plane shear strain. In-plane shear strain varies through the thickness z. Then this represents the twist curvature of this laminate. So, okay, we need to understand the again this uniform strain and curvature. And another things we need to understand is the load we apply. The load N1 is the stress integration through the thickness. One direction, two direction, and six direction. And then a moment. Moment is the we apply a bending moment in one directions and two direction, and also a shear direction. And there is a z multiplied by the stress, which means that the conventional definition of a moment. So again, in-plane load is just a summation of the stresses of each ply, sigma bar. Please pay really attention to a bar here. A bar means that the x-axis represent the each axis component, sigma 2 and sigma 6, and so on. So sigma bar is the important. And now we don't have the definition of this one yet. We will get back to you. I like to do some top-down approach to introduce these relations. So anyhow, this strain and NM, finally we have these relations and bending in-plane load and bending moment and in-plane strain and curvature. There's a relation ABBD, which represents stiffness in this laminate. So key point is that how to drive this ABD based on the each ply properties. So as the equation says, given load N and M, we will have a epsilon 0 and curvature. That is the strength. Okay, so we're gonna play with this to better understand this equation. I'd like to remind you that let's say we have a beam, very simple beam, or a bar under extension. So this is the say simple isotropic bar. Then if we apply the P here, there will be some strain in tension, and P equal EA epsilon. So EA is the stiffness in this in plane, and this is the bending. If we apply the bending, there will be some curvature, and between the moment and curvature, there's a bending stiffness. So in this case, we can say P and M, EA 0, and EI epsilon and curvature. Okay, this we like to represent this relation with a matrix and vector form. It's not a vector, but I would just call them a vector. And EA and EI is the stiffness. It clearly says the E is the stiffness of Young's modulus of each material, and A is the information of the cross section. And for the bending, same. This E is the stiffness, and I is the information about the thickness. So this is a very important relations. The most simplistic relations. It gives us the concept. Now, depending on these materials and layup, let's say, again, this is just a simple one dimension, like the beam. I'm sure this all of you are familiar with these relations. Now, depending on the some layups for the beam, something like this, and we may have a different material property like this, and different material property like this. Then this EA is no longer just one ply property. We can have some equivalent, some material stiffness equivalent to representing the stiffness and ply thickness information, and even further this. So I'll just show the head, I mean the bar representing the stiffness. So concept is that this term represent the material property information, and A means the information about the each thickness. Okay, that is the very important concept. And bending stiffness is the same thing. Now, depending on this the sequence, imagine that we top and bottom, okay, top and bottom, say E1, 2, 3, we have a aluminum and say any material, rubber or the bottom is steel. With a different material property and information like this, under tension, and you can imagine that this beam will not straightly extended. This can bend under tension because we have an unsymmetric material property. So under this tension load, this will extend it. Extension like that. Extension is represented by the epsilon here. I will use the epsilon. Oh, sorry, epsilon 0 here. Okay, epsilon 0 here. But also under this this load, this may deform like this. Well, aluminum is something like that. So under the tension, and we're gonna have not only extension, but also we're gonna have some curvature. Why? Because unsymmetric layup sequence. What does it mean in this? It means that in this equation, we're gonna have some terms P and K will be related. So there will be some, I will just call B. Some terms will appear, non-zero term will appear here. And also, if this say similar to this sequence, aluminum or rubber and the steel under bending, this will not only curved, but also it will have some extension. So under moment, we will have a relation with not only K, but also epsilon 0. So there will be some non-zero term appear. And this B and this B is physically has to be the same. Well, there are long verification procedures why this has to be symmetric, but I will skip that procedure. So there will be a off-diagonal term, B and B, and B and B here, and some term here. So as a simply, we can say B, P and moment equal. I will just say A, B, and B, D, okay? And epsilon 0 and curvature. So this is the for the beam, one-dimensional load and one-dimensional deformation. But if this is extended to a plate, now we will have not only this load, but also this load, okay? And also, since it's a plate, we're gonna have a shear strain, shear load as well. Okay, so one-dimensional to two-dimensional. If one-dimensional, we will have only P extension load, 2D and 1D, and 2D means that it's something like the plate like this, and then a load will be extended to a 3 load. I will just call N1 instead of a P, so N1. And then this load, I will just use N2, N2. And the shear load will be represented by the N6. There is some reason why we call N6, but main point is that the 1D, we only had a extension load. Now 2D plate, we're gonna have a 3 load. Pay attention, not just 2 load, we're gonna have a shear load. The shear load is very important. Now moment is same concept. Moment, we had only one moment, but moment will be not only if we have a plate like this, this gonna be we can apply the moment in the one directions, and then we can also load this way, moment 2, and then also we can twist. Twist is kind of difficult to visualize, but you can say this gonna be a twist. We represent twist this way. Okay, twist. So twist, if we apply deformations, you can see this goes up, and this goes down and down. So anyhow, we use the M6. So M6 represent the twisting moment. So from 1D to 2D, we have a 3 load and we have a 3 moments. And epsilon 0, same thing, epsilon 0, we're gonna have a 1 component and 2 component and 6 components. And here is the curvature 1 and curvature 2 and curvature 6. So this 2 by 2 matrix is gonna be a 2 by 2 matrix, but now this gonna be a 3 component, and this gonna be a 3 component, and 3 component and 3 component. As you can see, A will be now 3 by 3, and B will be 3 by 3, and B will be a 3 by 3, and D will be a 3 by 3. So totally 6 by 6 is gonna be 6, and multiply by the 6. Okay, this is the what we meant by the 6 by 6 matrix last week. So this one is already defined, but the main point is that how we drive this, we call ABD matrix, depending on the material property and sequence. That is the key point. Depending on the material property of each ply and the sequence. Sequence means that the order of plies. So material property and order of each ply will give us, will determine this ABD matrix. Okay, so let's assume we have a ABD matrix, and then we're gonna have a back to our Excel file. So as you can see, this is the load we apply. This is the number in blue, and inputs in blue and outputs in red. This is the convention we are using. So here we enter, and then here we're gonna have a 3 strain and 3 curvature. Okay, so the of course, if we enter 0, 0, 0, there will be no deformation. And this is the one, and any load, you can see that there is some output of a strain. Well, we don't know anything about the magnitude and values. We just like to understand the format of this program. Now, each ply means that is 1, 2, 3, 4. And now, as we can see, material number 4 means that now we have a database, say number 4. There is a lots of different material. We don't know anything, but don't worry, we have a certain name of the materials, and each one has the material number. So number 4 in this case represent the T700 H35 resin system, and it has some stiffness. And now very important point is that X directional stiffness and Y directional stiffness and Poisson's ratio and also shear stiffness, they are all different, as you can see. X means that the fiber directional stiffness will be much higher than a matrix direction or transverse direction, as you can see, more than 10 times. So this is sometimes often neglected, but very important to understand the ratio. So it is about the 140 gigapascal, and this one is about the 10 gigapascal, and shear is the order of 5 or 10 gigapascal, and Poisson's ratio is the same order as the 0.3 as noticed in isotropic material. Okay, so we just pay attention to this force stiffness. And here, one point I like to mention is that there each name we always have a slash AS for slash peak, T300 slash 5200. The first word represent the fibers. AS4, this is a carbon fiber, and T300 carbon fiber. T3 is also represent the T300, T700, and E-glass, and so on. The second name or second word represent a resin system. PK is usually mean the peak, and 5208 is the epoxy resin system, and 52 also epoxy system. So now it's kind of clear, but there is something like the Scotch. Scotch represent the very typical glass fiber. So this is the Scotch is a brand name, but become just a material name since it was a popular. So Scotch is the represent the glass epoxy, and also e-glass and some. You can actually define your own. IM7 is the carbon fiber 8551. So if you have your own composites made from some fiber and resin system, you can have your own. And here you have a steel is a isotropic steel. So this is the 206 gigapascal in S direction, Y direction. There should be the same, right? And then Poisson's ratio 0.6, and shear modulus is a 79.5. As you know, the isotropic material shear modulus is not independent. So 79. Actually, there is a equation equal this one divided by 2 plus 1 plus Poisson's ratio. This is a very famous. So as you can see, this is the same as the material property we have, and then we can change the color representing this is not the independent. This is going to be a dependent property. So in this case, we have a color, red color representing. I mean, we should not change the this formula. So anyhow, T800 is another Toray. Toray is the T700, is a very typical. This is the Toray carbon fiber. And this one is the also T800 also carbon fiber. As you can see that 139 versus 157, which is a much higher stiffness. And T700, T300, well, there's some different user defined. Don't pay attention to this. So anyhow, as you can see, very typical material properties you can play with is that this carbon fiber case, this is the one you can use, and then these two are, I mean, representing isotropic materials. Okay, so let's play with the steel. Okay, steel is a number 10. So number 10, let's say we have a force ply. Force ply represent from stacking from the bottom. That is our convention. Okay. I'm sorry, I made a mistake here, but the stacking is the from the bottom here 1, 2, 3, 4, 5. Okay, usually from starting from the bottom. So let's say again we go to apply and then let's choose a steel number 10. So if we just enter number 10, means that first ply will have a steel, and now angle is the one we need to understand that. But you would guess what it means by the angle. You know, the carbon fiber or any fiber will have a certain fiber direction. So this is the fiber direction as shown here. Now you can see that it's very important to follow the axis. This is the x1, okay, x1 and x2, and now this is the fiber direction, and y is the transverse direction. So all the material property is gonna be this direction, x and y. Okay, this is the x and y. All the material property will be here and this direction. That is the called on axis. And x1 and x2 x prime and y prime it represent, we call ob axis. Ob axis is, in other words, is the reference direction, but with respect to on axis, this is the ob axis. That's why the is called ob axis. But more conceptually, it is better understand. Ob axis is a reference direction. So we're gonna layer, and sometimes we're gonna have a different angles. And now this theta in counterclockwise with respect to this x1 and x2, this theta will represent a ply angle. Okay. So at the very bottom, you can start with 45 like this, and then second ply minus 45 can be like this, and the third ply 0, which means that you can layer like this, and then fourth ply can be 90. So 4 ply, for example, plus 45 minus 45 and 90 and 0. So this is the kind of stacking. We will get back to this sequence more to cover many different typical layups. Now, in here, each ply can be a fiber reinforced composite, but each ply can represent not just the composite, but can be also a isotropic plate, isotropic ply, like the steel or aluminum. So we like to say, okay, we choose 10, and then that means the material name is the steel. This steel, 10 name is automatically called from this, here. Okay, if we delete this just a steel, then as you can see here, it's just a steel. This is linked. Link means that, okay, material name, material number is this row, and material name is the here. As you can see, this range is called material. So this full range, the name has a name of the material. So as you can see here, material name. Okay, material, but it has a material name. As you can see, the first column represents the material name. You can read it here, right? So actually, what you can do is that you can select this much, and then up to here. Oops, not this much. Maybe okay. You can select here. You can have many names. Let's say material name. Okay, okay. Starting from first to up to here. Okay, this column, I mean this range is called has a name material name. As you can see, which one in this name you can say that material name, and then material number. Material number is we just entered the 10. So this means that 10th material number is the and this is the material name. Okay. Well, there is some option like the input type equals 0. Input type equals 0 means that where is the input type? Input type is whenever you want input type, you can click here, and if you want to know what is the input type, you can always select and trace the dependent precedent, which means that okay, this one there's a material input type 0. I mean this row is the input type, so it has a 0 there. I mean, what does it mean 0? Well, we don't have to worry about it. It is a 0. In that case, we from this input name we call here. So that's why we got this much this name. So what we like to do is that we have a isotropic still, and then is isotropic. The angle is not main point. You can enter 0, or you can enter any angle for the isotropic. Isotropic, in case of isotropic, angle doesn't mean anything. It can be 0 or anything. And now the third one is the material thickness. Material thickness. We just for the convenience, we just define the unit ply is a 0.3386, and then it happened to be twice. Or you just enter whatever you want to enter. Say 0.1. Always remember there is a unit there. In this case, we program that the thickness, the order, the unit is a millimeter. So the okay, 0.1 millimeter thick steel plate is a stack there, and then we can have as many as you like. Let's say whole price up to here. Okay, then as you can see that, oops. As you can see that each ply you can change it to a steel stacking, steel ply. Okay, and you can have many plies. Actually, you can see that it has a lot of columns, depend up to as many as plies we wish to consider. But you can simplify, you can reduce the number of plies. Say you just want to consider it's too many. If too many, you can just okay. Well, I don't wanna make it complicated. I just want to follow this one. And here, what if you don't only 10 here? Okay, we just enter one more. We have only 10 plies. Okay, 10 plies, but as you can see, all of them are steel and 10 ply, and each ply thickness is the 0.1. And then although if we want to neglect these plies, we cannot delete, but we can have a zero thickness. So whatever material, we can have a zero thickness. Zero thickness means that a way to eliminate this ply. So if we enter all zero here, means that we only have this 10 ply. Or if we only consider the one ply, just a steel plate, you can have a zero, you can have a copy and paste. So this means that we only have a one ply, steel plate, 0.1 millimeter thick, and then we apply this much load. Then we're gonna have a strain and curvature this much. Okay, so let's consider only 10 plies of isotropics. Then also we apply only 1 Newton, and others, let's say 0, 0, 0, 0, 0, only in plane load. And in this case, as you can see, we have a strain one direction. Oops, we have a strain in two direction and no shear strain. And well, this is the 10 to the minus 21 is a 0. It's just a numerical error. So no curvature. But pay attention to here, please. We have a minus in two direction. What does it mean? We have a so if we have a I'm gonna if we have just one ply, and also we apply the N1, this load. This is the 0.1 millimeter. And then deformation wise, what will happen? Well, certainly this is isotropic. This will be extended this much, right? Left and right. But also in y direction, there will be some contraction, shrink. I cannot call shrink. It's a contraction because of Poisson's ratio. This is how much extended and how much contract. This is the Young's modulus, and this is the thickness. So all matter of the Young's modulus and the thickness and also the Poisson's ratio. Okay, so well, it's very easy to understand in this case. Here we have a 10 plies. 10 ply means that we have a rather than just a 0.1, we're gonna have a times 10. So we have a 1 ply and second and third and so on. But it all still, so as you can see, this is the same as the steel plates, like the 1 millimeter, because this is a 0.1 times 10. It's the same material. In this case, the all steel, and this will be the same as the 0.1, the 1 millimeter thick. But instead of this, we prefer to analyze this one, because in each point we will have a strain as output. If we consider just 1 ply, then strain will be only this point, that point. Accuracy is okay, but the results, we're gonna have a finer results. Okay, so this is the a case study. So this is the steel, and now again here we only 1 ply, and then this is the result. How we calculate it? Well, don't worry, program calculate for us. And now we like to plot. Plot means that this is the okay. This is the vertical axis represent the z-axis. Okay, z-axis, and this is the one direction. As you can see, that the blue is what's the value here? Value of value of 0.00. So this represents the strain, the strain of this strain, the first one. Okay. This one, and then transport direction, we have this much is the output. So transverse and the 90 direction, we have a contraction minus, and shear strain is a 0. Okay, so this is called off-axis strain. So this is a one worksheet, but we can see that how this one shows the output, and as you can see, now we apply not only one direction but also two directions. So we apply this load. Okay, one, and what kind of deformation we're gonna have? As you can see here, this one, the first one, all one directional and second directional axis is the same. This is overlapped, and the shear is no shear strain. And actually, each one all has a stresses, and one directional stress and 2 directional stress and 6 directional stress. And the stress, okay, we will discuss about this a little later. And here also we have a vertically, we have a 1, 2, 3, 4, 5, and then we have a 11 dots because we have a 10 plies. So we can see each one would represent a ply, okay, through the thickness, and the x-axis represent the strain. So 1, 1. Now we can see why we have this much strain. And again, this much strain represents numerically, you can see here, this is the value. And now, of course, we apply certain load in shear direction. You can see that we have not only we're gonna have let me see. It's happened to be overlapped. I don't know what happened to other strain. Maybe this is not the. Okay, so yeah, I like to show them separately. So we enter or apply the 1, 2, 3, and as you can see, strain 1 to 6 is like this, and each ply will have a certain stresses. So this you can see that stress, same concept, and in all axis. All axis, on axis is the one you need to understand clearly. So this is a very fundamental and simplest case. Now we can apply bending moment. Let's say we eliminate no in-plane load, but only in-plane the bending moment. The bending moment, as you can see, we have a strain through the thickness. Now, again, one directional moment means that the strain will vary like this, and the strain is the a little bit opposite direction, but linear, and no shear strain. So this is the strain field. Okay. Now I'm gonna I will get back to these representations. Why we have this much strain. So this is the case 1, and this is the case 2. Case 2, we have a plate like this, and then we apply the bending moment like this. Actually, to be consistent, we have a downward or upward bending. So this is gonna be a curved like this. We can easily see that. Now that's why here is the one direction, or two direction, x2 and x1, and this is the z direction, x3, and we have a bending moment downward. I'm sorry, this way, moment 1. Now, moment 1, we can easily say the top surface will extend it this much. So this is going to be tension, and bottom one will have a contraction, negative. So as you can see, the one direction, we have a top, we have a positive and negative. Is a linear. So through the thickness, we can see that the top, the highest strain, and bottom is a contraction. So this is going to be plus and minus, and through the thickness, we have a linear deformation. But very important in this plate case, the okay, this top is extended this way. Then what will happen to second direction? You either have a contraction, right? This is gonna be a contraction, and the bottom this way is the contraction. Then this way will extend it. So to have a continuous deformation, we will have a contraction, and we'll have a extension. So this is the deformation. We can imagine this. Okay, this is the case of the under bending plate. Under bending, the deformation will be always like that. So this will have a curvature 1, and then also okay, this is the curvature 1, and now this one will have a what, curvature 2. Where curvature is always represented by the radius, inverse of a radius, inverse of a radius. So understanding this anti-curvature is very important, understanding our plate. So that's why this way we have a compression, and the and negative, and the bottom is the positive. So this is the this much. So each ply, as you can see, in one direction we have a tension, and the second direction we have a contraction. Why? This is the again because of Poisson's effect. Just consider on the top. And then, of course, there is a no shear deformation. So understanding this is important, and you can visualize it, visualize the deformation like this. And what if we apply the moment 2, same direction, moment 2, and this will, I'm sure the deformed will be like this, and will be like this. Okay, this is the deformation. If we apply the moment 1, moment 2 downward, then this deformation will be like this. So let's consider this is the case 3. Case 3 is the M1 and M2 equal non-zero. This is only M1 equal we apply, and this is the only N1 we apply. So case 3, how we can predict such a deformation? Well, very easy and very straightforward. You just apply here 1. Then as you can see, all positive, and one direction and the second direction is the positive. Is the overlap. I will just enter slightly different so that you can see the difference. Okay, so same moment, I mean same direction, and it shows that positive, but if we apply one direction, please remember we will have an anti-curvature. Okay, so this is the important point. Now, okay, again, I'd like to remind you that since we enter all zero, zero means that we don't have any layers. We only have 10 layers, okay? And each one is the 0.1. Now, let's say we are layering composites. Very typical one is the number 4, T700. Okay, this is the Toray T700 and number 4. So let's stack number 4. Now we have a T700 and just copy. Oops. And then even second and third, we just have a sorry, before that I have some other things. Sorry. We like to consider another case study. Okay, case. Another case is that we have a steel. Okay, we have a steel. This is a steel. And second ply, now we have a aluminum. Okay, this is the aluminum. This is the second case. And then let's apply to this load, N1. Okay, this is the another case study. Let's consider this one before going to composites. Okay, in that case, here the aluminum is the number 11. So we choose 11, but for convenience, let's choose the 5 steel and 5 layers of 5 layers of aluminum. Oops, what number was it? 11. Okay, 11. So the from here to here, we choose the all aluminum. So all aluminum here and all steel here. And then this is the layup sequence. Now we apply the just in plane load. Okay, in plane load 1. Now let's take a look at this case. Well, it's quite different from last case. Last case, we certainly remember if all still under in-plane load, there will be only uniform and one directions and the Parsons effect. But now here we only apply the in-plane, but it has the linear bearing. What does it mean? It has a curvature there. Its curvature will be caused. Means that if we apply the N1 like this will have a something like this, right? Something like that. And also we have an anti-curvature like this. Okay, so we can see that this is the curvature 1 and the curvature 2. Of course, this is the this much extension. Okay, this much extension. How do we know that? As you can see here, by number, you can see that extension and contraction and curvature and anti-curvature. And by we have a add them, and this is the final strain. Okay, so this is the case of the unsymmetric caused by the layering different isotropic material. So this is the case. Very important in laminate composites. Again, this is the even for different isotropic steel and aluminum, and this will cause the curvature even under in-plane load. Of course, if we apply a bending moment, okay, for this one, what will happen? Can you imagine that? It's important to be able to, this is the bending like this, okay, bending like this. Then we sure that we gonna have a strain, of course, the curvature, and also we're gonna have a curvature. See, again, this is unsymmetric, and moment we just apply moment, then we can imagine that there will be some moment and some a curvature, in-plane strain and anti-curvature. Now here, please pay attention. There in the zero, there is some strain here. What does it mean? Well, I just like to remind you that if this is the all steel material like this, and as you can see at the center there will be no strain. Means that if in the previous case where only the steel, then epsilon equal epsilon 0 plus z curvature, and this epsilon 0, okay, epsilon 0 in case of bending, or here epsilon 0 plus z curvature. So if epsilon 0, okay, this term will disappear for bending case, for moment case. So only curvature. In case of all isotropy, this is all isotropy case. Okay, so but if the layer has the unsymmetric, even with the isotropic, you can see that we have a non-zero strain at the center. Okay, so say I will get back to our aluminum layers here to here. Now, as you can see, there will be some point of shift. What does it mean? You know, again, if we have this, then epsilon equal epsilon 0 plus z curvature. You remember the z equal at the center, strain was not 0. What does it mean? On the bending, we have a epsilon 0. There will be some epsilon 0. So we will have this much is the strain, epsilon 1, and certain here is the epsilon 2. This is the so at the zero we have a certain value here. Okay, certain value here. What does it mean? This is a non-zero. So that is an important point. And here I just like to remind you that N and M and A, B, B, D, and we have epsilon 0 and curvature. I just use this 2x2, but this is the aluminum and steel. Then I call unsymmetric. Unsymmetric will cause the B. B is a non-zero. How can we say that? Well, as you know, if moment one cause not only curvature but also z epsilon zero. As notice that at the z equals zero, strain is not zero, means that we have this term as well. So for that one, we notice that B equal not zero. So this is the case. Unsymmetric, we apply only moment. We can see this is the case. Now, we didn't mention that, but here, this is the one we have a ABD matrix. You remember this one is the represent ABD matrix. Okay, this is the one ABD matrix. As you can see here, this is the called A matrix and B matrix and D matrix. Well, for now, forget how we got this one, how we program this. So we will learn step by step. But now we are top-down procedures. So we just learn how to use and how to how these metrics represent. So as you can see, A matrix. This one is the non-zero, as you can see here. So the let's say. So I just want to show you this. Okay, sorry, this one I'd like to show you. As you can see, please pay attention here. We have a non-zero B matrix. Some term is a non-zero, right? Why? Because this one is unsymmetric. 10, 10, 10 means still. But if we change it to all still, then let's see what will happen. Here, all still. Oh, as you can see, this become very small. This is again the numerical error. But as you can see, compared to other order, this is a very negligible. This means that B equals zero. In case this is the unsymmetric, is all symmetric, one plane or symmetric. Okay. Again, I will show you. This is the 11. As you can see, order is the order is a different. As you can see, that this is a not zero. And notice that this is all symmetric. This term is the same, and this term and this is term same. So this is the B matrix, and this is the A matrix, and this is a B matrix. Okay, so this is the observation, and also we observe that the strain has a non-zero. Non-zero here. Okay, here is a zero, so we have a non-zero strain. Now we can see why that it could happen like this. I'm sorry to continue without break because I need to like to close the class by the 5 o'clock or 5 or 10. Okay, so this is the how we layer the sequence, and then this is how we apply load, and this is the how we observe the strain. And also there is some strain distribution, and there is a simple plot. And this plot simply represent this epsilon and curvature. That's actually what we all we need. And numerically, we have a ABD matrix, and this is the nothing but we just enter the value, which is the same value we enter, and this is the ABD matrix. And then so point is that how we get this ABD matrix. Well, this is the key point of this classical linear theory. As you can always see that this is the how we get the A matrix, and this is the all the contribution of A matrix from each ply. And this one, how we calculate, Q11, what is the Q11? We don't know yet, but the Q11 times the thickness. So as you can see, this is the formula. And the present, you can see this comes from the ply information, and also some information about the stiffness. Stiffness is the here. Okay, so those theory in detail will be covered step by step, but we as a user of this tool, we just want to understand what will be the input and what will be the output. Okay, now let's go to composites. Well, we don't know much about the composite yet. But we know that composite consists of certain fibers in certain direction, reinforced plastic resin system. And as you can see, we have a certain, different stiffness along the fiber and transport direction and Poisson's ratio, and also shear stiffness. So here, let's choose the number 4. Let's choose the number 4. And number 4 means that here we have a number 4. And copy here. And all number 4. This is a simple way to choose the each ply. Now each one has the composite T700 epoxy, 10 layers. Each one will have a 0.1 millimeter. So totally we have a 1 millimeter because we have a 10 times of a 0.1 millimeter. We have a 1 millimeter thick. So this is a composite. All same angle, 0. Okay, same angle and 0. So again, we apply the moment, and we can easily see that we have a strain distribution like this, kind of similar to isotropic case, but material property in this direction and that direction is quite different. Now, when we apply the in-plane load, and is too small to show up here, but well, is still too small. Okay, and as you can see, it's too large. And as you can see, we have an in-plane, and on because of that, we have a curvature because of that. So we can immediately understand and then calculate how much we have a strain and curvature as we apply. Okay. And again, we didn't pay much attention to how much stress we're gonna have, but as you can see, this is the stress of axis, and this is the stress, and in on axis. On axis means the along fiber direction. Now each one can have a different fiber direction. Of course, this case is we have all the same fiber direction as a 0 degree. But now, as you can see, so stress, we need to understand the strain, okay? Strain and the stress. Um, I guess I just delete. Okay. Let me. Well, I just wanted to show the in-plane strain, but let's forget it now. But you can see there is a strain, on-axis strain. This is the off-axis strain. You can easily plot. Everything is on the value is on the left. Now, now we can we need to pay attention to the stress here. We don't know the magnitude response, but you can see this is a pretty much linear because we have all the same material and bending. We have a curvature and in-plane strain, right? So they will be all linear. Now, we like to give a certain angle, say 45, okay? 45 degree. All 45 angle. So even under very simple, okay, we apply 0 and 0 and 0. So it just imagine that we have a 45 price, okay, 45 degree, and same all up to 10 price. And now we can see under N1, we will have a very important point here is that we will have a strain one direction and two direction as a Poisson contraction, but we also have a shear strain. Okay, shear strain even under tension load. That's a very important behavior of this angle. Again, if we enter 0 degree here, okay, or 0 degree up to here, as you can see, shear strain will not be generated. But if we have a off-axis strain like that, you can see that we have a shear strain. And now another point is that let's say we stack the 45, 45, 45, and then now we enter minus 45, different angle. So like that. And now we have a strain plus 45 and minus 45 under in-plane load. And then this is the strain. Now from here is difficult to guess. See, the shear strain is a linear, and the tension and compression in each direction. And stress will be like this. Shear strain will be zigzag like this. And the off-axis, one is the tension, but linear like this, and then off-axis like this. So as you can see, it's kind of beyond, I mean, simple explanation. So for this kind of a complicated off-axis angle, sequence with a different angle. Now we have to look at the calculation and then get the value. So that's why this tool is very powerful. It can represent, it can calculate all the strain or stress even for many different ply angle. So another very important sequence is like the let's say quasi isotropic laminate. Quasi-isotropic laminate. What does it mean? What it means that we have this is a very typical quasi-isotropic on the left. 090, minus 45 and plus 45. And then okay, well, this is not okay. This one, 0 from the bottom, 0, 90, minus 45, minus 45, and symmetric, minus 45, plus 45, and 90, and 0. This is the very typical laminate used for the aerospace structures. That's why we call it quasi-isotropic laminate. Okay, quasi-isotropic laminate. And even for this, for this quasi-isotropic laminate, we can, well, by derivation is very complicated, but using this tool will be very simple and straightforward. How will you do that? Well, we just had this much the layup, and oops. All you need to do is just the enter from the bottom, 0, 0, oops, 0, and then a second, 90, 45, minus 45, and minus 45. Sorry. Minus 45. And 45. And 90. And 0. Okay. So how many ply? We have 1, 2, 3, 4, 1, 2, 3, 4. And notice that symmetric. Symmetry means with respect to a middle plane, there's a angle is a mirror images, right? There's a, and then only 8 ply. So how to neglect this one? We just enter the 0 for the thickness. So we neglect all others. Now this is a symmetric, and we apply one in plane load, and here we can see the curvature and strain. And the now let's take a look at the graph. Okay, this is the one we just have it. Okay, strain wise, we have a quasi-isotropic laminate, very complicated angles, and you know this is looks very complicated. And then on the simple extension, now the result looks very simple. In plane strain, epsilon 1 and epsilon 2 and 0 strain. Oh, this is very same as the old steel laminate ply laminate. Actually, there's a theory that if we have a 0, 90, plus or minus 45, and minus 45 and 90, 0, this is all 45 angle apart, and which is called quasi-isotropic. By name, it means that quasi-isotropic, behavior like the isotropic. So that's why all strain is like this. But stress is a quite different story, because in each direction we have a different material property because of a different angles. different angle give us a different property in each direction. So that's why very complicated stress of axis and even the on axis. Okay, this is the stress and strain. So that is the case. Now we need to observe that, but so this is the one under in plane. I mean, imagine how it can be complicated when we apply the certain load, like this much load and this much load and certain bending moment. Even here, any bending, any twisting, bending, whatever, which give us all the strain variations and also stress variation through the thickness and off axis and on axis. You can see that how complicated it can be. But no matter what layup sequence, angle, and material property we choose, always the strain is linear. That is a very important observation. So we had a certain very simple extension. Will have a very much a uniform. Uniform means through the thickness, x direction and y direction. Now stress will be quite different because we have all different layup sequence. Now here a very complicated load and bending or whatever. So we could have this much complicated. But no matter how many sequence and angles, or no matter how much load we apply, always the strain, observe that strain is very much linear like that. Why? Because we start with a theory always like this. So strain, I mean, all the three component strain is always z through the z means that this is a linear, constant and linear. So that's why we have always a linear through the thickness. But since we have at the z equals 0, z equals 0, we have a strain, which means that here we have a non-zero strain, and non-zero strain. At here is at equal z equals 0, right? Since it is a z-axis. So this is the case isotropic case. Of course, this quasi-isotropy is very limited, very special case, which are mainly used for the aerospace structures. But we, as a designer, we can certainly have a freedom to choose any angles we like to choose. And of course, you can see that for the biaxial laminate, something like plus, minus, plus, minus. Well, this is the very much typical case when we make the pressure vessel like this, and we have a layup like this, and layup like that, and layup like that. So whatever in the middle, we have a biaxial laminate with a certain angle theta. So this one we call plus minus theta, okay? Doesn't have to be symmetric. This is another case. So this will be a axial laminate. Well, how we consider this one? Well, this one, I would say, let's just start at 45, minus 45, and just repeat. Plus, minus, and up to now, okay, just consider 8 plies. Okay, so plus 45, minus 45, plus, minus, and then each ply thickness. And then whatever load we have. We have a load, say just one load like this. And then you can see that you will have some strain like this. But as you can see, we have a very much alternative layer. You can see the stress is a zigzag, and plus minus, and very hard to imagine. I mean the estimate the value, but you can see why we have the zigzag kind of fly. Now, just one theory very important is that equivalent stiffness. You know, we have a laminate, but we can imagine the equivalent stiffness in one direction and two direction, and Poisson's ratio and the shear stiffness. This equivalent stiffness, okay, stiffness of the laminate. I don't have to define, but we can imagine that we have a properties can be defined as like this. So we have a laminate, and then inverse, and by definition of a engineering constant, we can define like this. So and it has a very special feature. Now, this is the one of the key function I like to emphasize. Here, we have an input. Input is the, pay attention here, you have an input here, okay, input. And then this is the equivalent of stiffness. Input, what is the input? Say this, I would like to change this is as an input, okay? And then this will be a 90 degree. Why? Well, simply because we have a input as the 90. Now, to represent angle of a biaxial, well, I will change it to 45. So this one will be a 45. Now, how to make the plus minus 45? Simply minus input, right? And then copy and paste up to here. So as you can see, plus, pay attention here, plus, minus, and plus, minus. Okay, so the so if we see here, if we pay attention, please here, if we change the like the 65, and this angle will be automatically changed like this. And then, well, this can be 25 and etc. Now, this is a macro to use to iterate all the cases. So if we like to change the 25 and the strain, I mean the stiffness, and equivalent the stiffness and so on, then if you click this, input value will be the input can be ranged from 0, and final is 90, and the step value like the 5. And then for each one, we like to calculate epsilon E1, stiffness, and etc. So this is the case 1. I will call case BX. BX means the biaxial. And click here and this, and then click. Now, as you can see, input file, the output file case BX is automatically generated. Why? Because we enter the name case BX, and 90, this input value, as I mentioned here, we changing from 0 to 90 by step value 5, and then this output will be automatically calculated. So as you can see, 0, 5, 10, and this 1, 2, 3, 4, 5, 6 is automatically calculate and then plot. That is what this macro means. Again, this one, we don't know much about the, sorry. Now here, again, what does it mean, this epsilon 1? I mean, this is the epsilon 1 equivalent. We didn't, so this is the stiffness, okay? This is the Young's modulus, but we would have a certain, whatever layout, we have a load and deformation. This is the Young's modulus equivalent stiffness. And equivalent stiffness, like here, we have a theta minus theta, and we have a theta minus theta, and this is the biaxial theta. And if it's a zero angle, we have a very high stiffness, because as theta equals 0, we have a this much layup, right? So if we have a 0 and etc., and as you can see, this is a drop like this, and this direction, there will be a opposite with a symmetry with respect to a 45 degree. So this is how we simply use this. We call it quick chart. Okay, quick chart. Input can be anything. You can input as a you can enter input here. You can enter input anything in this area, and this area. So this is the what we're gonna cover. Okay, well, today we just covered how to use this tool. A tool called HY means the Hanyang Classical Laminate Theory version, whatever number we have here, version 311, and the this is a kind of a complicated procedures and all the theory in there, but more important point is that what will be the input and what will be the output to understand the laminated composite case. Okay, so this is the what we like to cover today, and this tool and the lecture notes will be shared with you. I'm sorry I didn't share with you yet, but I will do that. But for anytime I will record. I didn't upload the last week course, which I will do that. So I will upload today's class, and together I will share with you this lecture note and this tool. Okay, well, again, this is what we like to cover, and this is the, if you have any question, please leave a message in the Kahoot. Okay, well, thank you so much, and then keep in touch.
예, 감사합니다.
네, 감사합니다.
감사합니다.